Welcome back to Ubad's lab, and today we're going to be looking at a problem that involves the conservation of mechanical energy of a rolling object. Alright, so we're going to start off by drawing a little diagram here. So we have a ramp, a car going down the ramp, and it actually has 4 wheels, 2 wheels on this side, 2 wheels on the other side that we cannot see, and then the ramp has a height of h, and the car, this top part of the car has a mass of m, and each wheel has a mass of m over 4, and there's 4 wheels. Okay. So our question is asking us, let's say this is all the information that we're given. We're also given that the radius of the tire is r. Okay. So with all this information right here, we can solve for the velocity of this car at the bottom. So it's released from rest at height h, and we're asked to find the velocity of this car at the bottom. And this car is rolling without slipping. Okay, so it's important to understand what type of friction there is. There's static friction, since the object is not slipping against the thing. It's as if when the tire is rolling at it, at each point the tire is making contact perfectly and not slipping. So there's no loss in dissipative forces, so we can use the conservation of mechanical energy to solve for the velocity at the bottom. Okay, so let's set 2 points. Our first point will be point A, which is where it starts, so this would be point A, and point B is when it reaches the bottom, so this would be point B. So we can do U, the potential energy at A, plus the kinetic energy at A is equal to the potential energy at B, plus the kinetic energy at B. Okay, so now let's identify what type of potential and kinetic energies we have at both points. So over here, the object's at rest, so we know that there's no kinetic energy. We can cancel that out. And we set this as our h equals 0 line, so it will have potential energy as h, and that will be gravitational potential energy. So we'll do U grav, which is our gravitational potential energy, is equal to our potential energy at the bottom. We have a h equals 0 line, so we can't have gravitational potential energy. There's no springs involved, there's no elastic tension, anything of that sort, so no potential energy at the bottom. We do have kinetic energy, but we have to identify what type of kinetic energy we have. We'll actually have 2 different types of kinetic energy. We have our translational kinetic energy, which is obviously the object moving, right? And if this was an object without wheels, so that the object was just simply sliding with no friction down the ramp. Oh, and something good to understand is that this has friction, because the only way for something to roll is through friction. If you had a wheel on a surface that was frictionless, it would just slide and not rotate. So this has friction, and that's what's causing the wheels to rotate. So we have the car itself translating, so we have that kinetic energy. Then we have the wheels rotating, so we have rotational kinetic energy, and we have translational kinetic energy. So K trans plus K rot for translational kinetic energy and rotational kinetic energy. So what would our gravitational potential energy be? it would be the mass of this entire thing. It'd be mgh, that's gravitational potential energy. But what would our m be? Our m would be the mass of this, right, plus the mass of the 4 wheels, and each wheel is m over 4. So the mass of all the wheels in total is just m, and the mass of the box is m, so 2m times gh. That is our gravitational potential energy, and we set that equal to the translational kinetic energy, which is 1/2 mv squared. So we do 1/2, and what would our m be? Is it just the box that has translational kinetic energy, or is it everything, including the wheels? So it's going to be everything, including the wheels, because the wheels are special because they have both types of kinetic energy. It has the rotational and it has the translational, so it's moving and it's rotating. So all of this mass has the translational kinetic energy, which is 2m. So we put it 2m and then v squared plus our rotational kinetic energy, which is 1/2 I omega squared, where I is our moment of inertia of the wheels. So that's basically the resistance to rotation. So just as mass is the resistance to movement in the translational world, a moment of inertia is like the resistance to rotation in the rotational world. So we go 1/2 our I. So what would our I be? So this is just something we could derive it, but that would take too much time. But the moment of inertia of a disk, let's assume that these wheels are just disks, not cylinders of any sort. So we're just gonna assume that they're a disk. So if they're a disk, the moment of inertia is 1/2 mr squared. So 1/2 mr squared. What would the mass be? The mass, what has this moment of inertia, this what's rotating? Only the wheels. And what's the mass of the 4 wheels? Each wheel is m over 4. There's 4 of them. So the mass of the wheels is just m. So the moment of inertia is just 1/2 mr squared, just plugging in m for the m. So we have this 1/2, and then we have to plug in 1/2 mr squared. Okay, that is that's the I, the moment of inertia, and now we have to do our omega squared. So let's just omega is rotational velocity, so velocity in the rotational world. So kind of the speed at which it's moving in respect to the radius. So, and then this is squared. So as you can see, this mimics our 1/2 mv squared in the translational world. So 1/2 and then mass, but this time inertia, and then v squared, but this time omega squared. Okay, so we have 2 mgh. We'll just write that down again. Let's do some simplifying now. These will cancel out, so we just get mv squared plus, we'll multiply that out, we get 1 over 4 mr squared. And omega, if there's rolling without slipping, one thing that we can do immediately is say omega is equal to v over r. That's only if there's rolling but without slipping. So there's only static friction at play. So mr squared, and we can immediately just distribute this squared. So if I plug in v over r into omega, we get v squared over r squared. Let's do some more simplifying. Oh man, I love variables. All right. Let's keep this mv squared plus 1 over 4. Cancel out the two r squareds. We get 1 over 4 mv squared. So now we have mv squared and 1/4 mv squared. So we can go 2mgh is equal to, this is basically like a 4 over 4 mv squared. So adding the we get 5 over 4 mv squared. And we want to solve for our velocity at point B. So another fun thing that could happen right here is that m's cancel out. We have m's on both sides. Alrighty. After that cancels out, what do we got? Okay. Let's okay. So we can multiply both sides by 4 over 5. Multiplying this by 4 over 5 will make it 1. Multiply this side by 4 over 5. So cancel that out. Multiply this by 4 over 5. We get 8 over 5. GH is equal to v squared. So now we square root both sides and we get our final answer of v is equal to the square root of 8 over 5 GH. There it is, our velocity at the bottom.